So let's start with a quick refresher on balancing redox reactions. So this is kind of the general method here that when we're balancing a redox reaction, we want to separate the oxidation and reduction half reactions and work with those individually before we put them back together again. So we can separate our half reactions first. And then for each of the half reactions, you always want to start by balancing for mass. So that's balancing the number of atoms of each element on each side. You always want to first balance things the normal way, as much as you possibly can. Adjust your coefficients to balance as many different elements as you can. And then only if oxygen or hydrogen remains unbalanced, do you need to go on to these second steps. If you still need to balance oxygen and you can't do it just by adjusting coefficients, you add H2O as needed. And then if you need to balance hydrogen and you can't do it just by adjusting coefficients, you add H plus as needed. So do keep in mind that that is H plus, that is a positive one charge, because that's going to come into play in the next step, where we're balancing our half reactions for charge. So we balance charge by adding electrons so that the charges are equal on both sides. So you're always going to be adding electrons to whichever side has the higher charge to bring it down to be equal to the opposite side. So at this point, both of your half reactions should be balanced. And the only thing we need to do before we can combine them is to equalize the number of electrons lost in oxidation with the number gained in reduction. So we can multiply our half reactants coefficients by whatever factors we need in order to make that true. And then we just add our reactions together and cancel out anything that appears on both sides. So I'm going to go through an example. If you would like to try this on your own, pause here and do that now before I proceed. So to balance this reaction, first thing we want to do is separate out our half reactions. So we're going to want to figure out what's being oxidized, what's being reduced here, and we can do that with oxidation numbers. So in the permanganate ion here, the MnO4 minus, oxygen is going to have an oxidation number of -2, which makes manganese +7, since we have 4 oxygen atoms, each at -2, and we're aiming for a sum of -1 overall. Our chloride has an oxidation number of -1. Manganese over here is +2, and chlorine in Cl2 is 0. So we can see that manganese is changing from +7 to +2, which is a reduction since our oxidation number is decreasing. And then Cl minus is going from -1 to 0, which is an oxidation since our oxidation number is increasing. So now we can separate out our half reactions. So our reduction was MnO4 minus to Mn2 plus. And our oxidation was Cl minus to Cl2. So first thing we want to do with these is to balance them for mass. So we want to do as much as we possibly can by just adjusting coefficients. In our reduction, we have 1 manganese on each side, so that's great, no adjustments there. We have 4 oxygens on the left and none on the right. We can't fix that with coefficients. We'll come back to it in a sec. In the second one, we have Cl minus on the left, Cl2 on the right. So we have 2 chlorine atoms on the right and only 1 on the left. We can fix that by putting a coefficient of 2 in front of Cl minus. That oxidation half reaction is now balanced for mass. We're not going to need to do anything else to that. So the next thing we need to do is finish balancing the reduction half reaction. To balance oxygen, we add water. we need 4 oxygen atoms, so we need 4 water molecules. We've now introduced hydrogen as well. 4 times 2 is 8 hydrogen atoms. We use H+ to balance hydrogen, so we're going to need 8 hydrogen ions on the left. And now this one is balanced for mass as well. So to balance for charge, we need to consider what is the total charge on the left and what is the total charge on the right in each of our reactions. Currently on the left, we have +7 because we have 8 positive charges and 1 negative. On the right, we just have this +2. So our total over here is +2. So in order to make these equal, we're going to need to add 5 electrons to the left-hand side so that now the total on both sides is +2. We have 8 positives and 6 negatives on the left, giving us +2 overall. Down here, we have -2 on the left and 0 on the right currently. So we will need to add 2 electrons to the right in order to finish balancing this one, giving us a -2 charge on each side. So at this point, this is where we need to make these numbers of electrons equal, which currently they are not. The simplest way to do that for this one is to multiply our reduction half reaction by 2 and our oxidation half reaction by 5 so that we get 10 electrons on each side. So if we multiply our reduction by 2, we'll have 10 electrons plus 16 hydrogen plus 2 permanganate forms 2 manganese 2+ plus 8 water. And then in our oxidation reaction, we're multiplying everything by 5. So we'll have 10 Cl- forms 5 chlorine and 10 electrons. So now we have 10 electrons on the left, 10 electrons on the right. Those are going to cancel when we go to add everything together into our net reaction. So at this point, we're just taking everything on the left and combining it, taking everything on the right and combining it, canceling out anything that appears on both sides, which in this case is just our electrons. So on the left side, we're not going to need the old versions of these. On the left side, we will have 16H+ plus 2 MnO4- plus 10 Cl-, and that is producing on the right 2 Mn2+ plus 8 H2O plus 5 Cl2. And that is our complete and balanced net reaction. Note that it doesn't matter what order you write the reactants and products in. I usually just put them in whatever order they ended up in my half reactions, but it doesn't matter at all. So that's the process you want to go through whenever you're balancing a redox reaction. Some are simpler or more complicated than others, but it's always exactly the same process.